Hello there. In this session I'm going to introduce you to the Pure Mathematics section of the Further Mathematics A-level course. So to get a full grade in the Further Mathematics course at A2 level, there are two papers that all students are required to sit in pure mathematics. So at AS level, you've got Unit 1, which have got the subjects as I've listed here. There's probably nothing here that you would have seen before, even in the additional maths qualification if you studied that before. Complex numbers possibly in relation to solving quadratic equations. You may have had some exposure to that, but the topics here are definitely beyond GCSE, and also the topics here you do see are quite distinct from what you study in the regular A-level mathematics course. And then in A2 level there is another paper, Unit 4, which all students are required to sit, again with the list here of the different topics. There's quite a lot. It's a substantial paper. You can see there are things like calculus, differentiation and integration again, which usually bolsters what you've learnt in your regular A-level maths course and helps it greatly. But again, there are quite a few topics here that you will not touch on at A-level at all, so quite distinct. So in this session, I'm just going to give you a flavour of two topics from the AS course, hopefully to spark an interest and something you haven't seen before. The first one we're going to look at are using matrices to describe transformations in 2 dimensions. This is something you've definitely seen at your GCSEs when we're transforming shapes on a XY coordinate grid, but now we're going to take it one step further and you look at matrices to do these. And then to completely change the type of mathematics, I'm going to look at some algebra and working out the formula for the sums of a sequence of numbers. So very much further mathematics, and I hope it does give you a bit of a spark to see the sort of stuff you will be doing, as well as a lot more. Okay, so let's have a look at some matrices then. So what's a matrix? A matrix is a rectangular array of numbers, which is what you're going to be seeing more, but they could be expressions, algebraic expressions or symbols. But here are some examples. It is literally just some numbers wrapped in curly brackets. That's your standard typical matrix. So this has got an order of 1 by 2, so 1 row by 2 columns. Here's another matrix. This has got 3 rows by 1 column, so it's got an order of 3 by 1. Here we've got a 3 by 2 matrix, and this example is a 2 by 2 matrix. And note, all different numbers can be put in there, decimals, negatives, fractions as well. The key is it's just a group of numbers, as you can see here, in an array. So, although you study matrices in pure maths in the further course, they are actually used extensively in many different areas, many different fields of science and engineering. So, in economics, they're used a lot because they're used to predict market trends, modelling, heavily used in the city, in the hedge funds, very powerful tool for making certain predictions, very difficult maths that you would be specialising in if you did economics. Engineering, again, in engineering there are many equations that need to be solved. maybe simultaneously, and using matrices, you are given certain tools to be able to do this. We in A2 of the further course, you will actually look at solving simultaneous equations, a set of 3 with 3 variables, which opens up a whole new different level of possibilities to what you've learned before when you've solved 2 in your GCSE course. So used a lot in engineering. Again, in business, certain decisions and making complex decisions can be put into a matrix, and then these can be manipulated mathematically to get certain results and predict or prioritize certain tasks. Chemistry, again, analyzing chemical equations. They can be used to describe the structure of crystals. Very, very important in computer graphics programming, which is what I'm going to touch on in due course. But yeah, matrices are used extensively, and I personally, at one point in my past, did some graphics programming and studied it, and it was the matrices that I had to use quite extensively in my programs. In computer security, they are used, as well as genetics. Physics, they're extremely important. All the particle physics that you may, if you do go on to study physics, in the physics of the small quantum mechanics and in particle physics, matrices are used to describe these fundamental subatomic particles and how they behave. And very much of the time using epidemiology for modeling disease spread. So yeah, matrices, and there's so much more, and it's a very, very important mathematical tool which is applicable to many fields. Okay, so first I'm going to show you how to add and subtract matrices, and it's very straightforward. So the first thing is they've got to be conformable. So what do I mean by that? Well, for example, if I add 2 matrices together, the key is they've got to have the same order. So then each element in the 2 matrices can be then added or subtracted to give me the element in the same place in my resultant matrix. So if I look at the top left hand corners, you can see you've got a 2 and an 0. A 2 add 0 is obviously 2, which is what I get as my answer there. So if I work across, you can see quite simply that by adding or subtracting using basic number arithmetic, you get the answer at the end. It's exactly the same for subtraction. Here again, the 2 matrices are conformable, so I can subtract them, which gives me the answer there. If I look at this one, I can't do anything here because I've got a 2 by 2 matrix and a 3 by 3, so there's no way of me adding these together, which I think seems quite natural in this case. So how would you do it? It's definitely not possible. Okay, so matrix multiplication is actually a bit more tricky. So let's first lay down the basic rules of how I can do it. So if I've got 2 matrices and I multiply them together, then you can see that the number of the columns of my first matrix must equal the number of rows of the second one. Okay, so we'll have a look at an example in a minute. And then what you find is the answer will be the same as the number of rows in A and the number of columns in B. So first off again, in A, the number of columns must match the number of rows of the second matrix to be able to multiply them. And then the final answer is the number of rows in the first by the number of columns in the second. Now, what's interesting about matrix multiplication is they are what we call, it's not commutative. So it does matter which order I multiply them together. That is very important, because not in the way with numbers where we know that 2 times 3 is the same as 3 times 2. It doesn't work like that with matrices. You will, generally speaking, get a different result, but that isn't always the case, depending on what sort of matrix you multiply by. So you've got to be careful with that. That's a very important result that you must remember. Okay, let's have a look at an example. So I'm going to multiply that 2 by 2 by that 2 by 1 matrix. Right, so first off, let's check that we can do it. So that 2 by 2 matrix, you've got 2 rows, 2 columns, clearly. In the second matrix, it's a 2 by 1. So as you can see, I've specifically highlighted those numbers green, they match. That's the key. So if they match, I can multiply them. And what I get is, let's just have a look at the size of our answer matrix, and then we'll work out how to do it. So now you can see that it's the first number of the order of the first matrix, the 2, and the 1 of my second matrix. So the size, the order of that matrix is going to be a 2 by 1, as you can see there. Right, so how do we get the 53 and the 47? Now, here it is. So let's just have a look at this diagram. So what you do is you look at, I'm looking at the moment at the 1, 6, the first row of my 2 by 2 matrix, and I'm going to then at that multiply that onto my 2 by 1 matrix. So look how it works, and if you follow the arrows, it's quite clear what we've got to do. So it's going to be the top 1 times by the 5, and then I always add the second number, which is the 6, times the 8, and that gives me the top number in my final answer matrix. If I go to the second row, so 3 times the 5, so you're always multiplying across the matrices, and then you add as you work your way down. So 3 times 5 is the 15, and then 4 times 8 is 47, and that is placed in the bottom. So that's how I would do this 2 by 2 times a 2 by 1 matrix. Let's have a look at this second example, which I've got my second matrix is a 2 by 3. So again, the first thing I've got to do is I've got to check if they can be multiplied. So the first matrix again is a 2 by 2. The second matrix is a 2 by 3. Okay, columns in the first match the number of rows in the second, the green 2s, so they can be multiplied together. And then the answer, the order of the answer matrix are the red numbers. It's the 2 rows by the 3 columns. And if I do multiply them together, there it is. So you've got the 2 by 3, and there are the answers for each element in the matrix. So how does this work? So again, at this point, here is the diagram. You may need to stop that and just have a look at how it works, but it's actually it's quite clear. The key with matrix multiplication is it's very error prone. So you've got to be really careful when you do it. It's quite easy to make silly arithmetical mistakes when you're doing this. It's just interesting. You've never really done two-dimensional arithmetic before, so it's a bit of a new thing. And yeah, the key is to make mistakes. But now on the new calculators, you can check your answers. If it was an exam, there would be required usually some sort of workings out. But with the calculator, you can actually check and multiply matrices together to get the right answer. So look how it works. So again, it's always I look at the first row of my first matrix, and then what I do is I go across the columns of the second matrix to fill out the numbers of the top row of my answer matrix. So again, you can see that 3 times 3, 5, and the 6, 1. That's the first thing I do to get the 23 in the answer. So again, it's 3 sixes, add 5 ones, there's a 23. Then I go with, again, it's the first row, but I've got to do the second column of my second matrix. So you got 3 sevens, add 5 times 8 is equal to 61. So you keep going through. So then you've got one more element to fill out from the first row, and then I go to the second row of my 2 by 2 and do exactly the same thing. So if you stop the video here and look at it carefully, you should be able to see how that works. Okay, I've got a little exercise for you to do to practice your matrix multiplication. So I've got matrix A, matrix B, and C, and I would like you to work through these sums, where, remembering I said that the order is important, so I want you to write down those matrices in the order that the question states, and I want you to work out the final answer matrix for each. If you want to stop the recording now before I show you the answers. Here are the answers. Okay, there's two more that I would like you to work out very quickly, which is this one and this one. So if you want to stop the recording quickly now and work these out. Okay, so what you should have found is, if you do those multiplications, you can see that multiplying any 2 by 2 matrix by 1, 0, 0, 1, and in this case it doesn't matter which order you do it, you actually just get the matrix on the left. So this matrix, the blue matrix, the 1, 0, 0, 1, basically any matrix with the leading diagonal, the diagonal going from top left to bottom right, it doesn't matter how big the matrix is, as long as it's a square matrix, same number of columns and the same number of rows, it is called the identity matrix, and it is an important matrix, and this is basically equivalent to us multiplying any number by 1. It doesn't change the result. So just so you're aware of this important matrix, the identity matrix. Okay, so now that I've taught you how to multiply two matrices, it's going to get interesting. Now we're going to actually use them to transform shapes, and you should be able to see the scope of this and why it is powerful, and why computer programs like your computer games would probably use this type of mathematics in their code. So yeah, this is really some good, interesting stuff coming along. Right, so I'm going to reflect a shape. It will be a triangle in the line y equals x. So far in your GCSEs, you would have been given a question like this, and you would have been told to do it and using words to actually do the transformation. But we're going to learn how to do it by using mathematics to do exactly the same. So here is my set of axes. There is the line y equals x. And what we're going to do is we're going to reflect that triangle with those coordinates on the line y equals x. Okay, so you can probably, hopefully, see where the answer is going to be, but I'm not going to use any words, any descriptions on how to do it. We're just going to use a particular matrix to do it. So the first thing you do is you put down your coordinates into a 2 by 3 matrix, 3 columns along, because it's a triangle. If it was a square or a rectangle or any quadrilateral, actually, you would have a 2 by 4 matrix. So the number of coordinates you've got on your polygon is the number of columns you're going to have in your matrix. And you can see it's color coded, so you can see how they are placed. Right, so what I'm going to do now is I'm going to multiply it by this 2 by 2 matrix. Now, I've just talked to you about the identity matrix. If you look carefully, this isn't, because the leading diagonal isn't ones, they're actually noughts. But if I now multiply those two matrices together, what you get is that matrix. And if I plot those coordinates, so again, lifting the coordinates from the columns, if I plot them, you actually get your reflection of the black triangle. So as you can see, all I've done is use matrices here to do exactly the same transformation, which is a reflection in the line y equals x. So very clever. So the key is, why is it that matrix? Why can I use this particular matrix to do the reflection of the line y equals x? Now this method is for the basic transformations. So there are different things you can do. To make more complex transformations is a different technique, which we will be looking at as well. But I'm going to show you how to do this for the basic transformations, which is a very useful way of doing it. So here again, I've got my axes. So what I'm going to do is I'm going to put what we call the vectors I and j, we call them usually, into a 2 by 2 matrix. So I've got these two column vectors, 1 naught and 0 1. And as you can see, that is the identity matrix. So what do I mean by that? So if you may or may not have seen vectors, well, actually you've seen it when we're talking about translating shapes. Again, in your GCSE course, you know that a translation was represented by a column vector. So 1 naught would have mean going 1 to the right. If it was a column vector 0 1, it would mean you'd be going 1 unit up. So these have got special names. It's the I and J vectors. So here it is. Here's my I vector, represented by this arrow, and there is my J vector. So what I'm doing is I've got these two vectors and I've put them into the matrix, as you can see there. Right, so what happens if I now reflect these two arrows in the line y equals x? Well, if you can see, the blue arrow, my vector 1 naught, is now reflected to point up on the y-axis. So that vector now becomes 0 1. And in turn, my red column vector, the j vector, which is going up along the y-axis, is now reflected on the mirror line y equals x to go on to now point in the x direction. So basically they've swapped around, and that's because it's the reflection in the line y equals x. Now the resultant column vectors you get from your transformation is what we put into the matrix, as you can see here. So can you see how my blue, the 1 naught from the original identity matrix, now becomes the blue 0 1? And exactly the same is what I do for my red arrow, which now becomes the vector 1 naught. So the resultant vectors you get from the original identity matrix, when you put them into your 2 by 2 matrix, that is the actual transformation matrix that will now reflect any shape along the line y equals x. Right, I'm going to show you another example now, which is how we're going to work out the transformation matrix for a 90-degree clockwise rotation about the origin. Right, so again, I do exactly the same thing. There in me, I'm showing you visually what's going on. So I start with my identity matrix, which is a combination of my I vector, which is the 1, 0, and the j vector, which is my 0, 1. And I'm now going to imagine what will happen if I spin these arrows around clockwise 90 degrees about 0, 0. So what does happen to them? So hopefully you can see that the blue arrow, now turning it down 90 degrees clockwise, becomes an arrow pointing down. Now the vector for that therefore is 0, -1. What happened to the red vector? Well, that now again is spun now 90 degrees and becomes 1, 0. So there they are. They've both been spun around by 90 degrees. I think it's quite obvious. But the clever part is that putting these two new vectors into our matrix does actually give us the matrix that will transform any shape by turning it 90 degrees clockwise about the origin. So here it is. Let's have a look at a particular triangle. So there it is. I've got the same triangle as before. I put them into my 2 by 3 matrix as columns. We've just worked out what the rotation matrix is. So if I multiply those two matrices together, I get a matrix, as you can see there. Now these are the coordinates taken from the matrix, and if I plot those points and join them, you will find that you actually get the triangle rotated by 90 degrees clockwise about the origin. Now I hope you can see how clever this is and how powerful it is, but also how simple it is. Once you've just established the vectors and understand how they work, it is actually very, very, well, I wouldn't say simple, but quite natural to see how all these different transformations are put together. So we're going to have a look at, I want you to have a go at a few and see if you can work them out. So here's the exercise. So I want you to, I'm going to list a few transformations for you. There is the triangle with those coordinates that I would then want you to transform. If you want, you can on your own square paper, if you want to quickly plot them to see it working, that would be useful to actually visualize it. But here they are. What I want you to do is I want you to work out the 2 by 2 matrices for these particular transformations. And once you've done that, I want you to use them to transform that triangle. So if you want to stop the recording now before I show you the answers. Here are the answers. Note how I've not shown you about the scale factor of enlargement at the bottom, but if you visualize it, basically the two arrows are twice as long, aren't they? So from being 1, 0, you get to 2 noughts for the x direction and 0, 2 for the y. Here is another exercise I'd like you to have a go at, where I'm actually giving you the matrices. I want to see if you can work out what the transformation is behind them. Here are the answers. Now, although I've shown you some basic transformations, this can be taken to, for example, with a rotation, I can actually do it for any angle. So you can see the power already here of using matrices. If I use that 2 by 2 matrix with the cos and the sine trig functions, as you can see there, you can actually spin a shape any angle you want by using that matrix. So you'll be looking at that in more detail in your further maths course. And again, with the reflection, this is really clever. Y equals x is quite easy, and you could actually draw that. But if I said to you, oh, reflect the line reflector shape on the line y equals 2x or 3x, if you think about that, the angle is not easy, and by just doing it by sight, or as you've done back in the day with tracing paper, it would cause quite a lot of difficulties. Whereas now I can actually accurately work out what the matrix is, and therefore where the coordinates will be of a reflection on any line. So again, this is something you will be looking at in detail in your further maths course. Furthermore, you may have been questioning, well, how can I translate a shape? We've done the other 3 transformations, but obviously you can translate a shape, slide it as well. Well, there's something else we've got to do in this case. Again, you will be looking at this. So if I wanted to translate a shape by 2 in the x and 3 in the y, what we've got to do is use something called homogeneous coordinates, and you suddenly have to work with a 3 by 3 matrix to do this. And there it is. That would be the matrix you would be using, and then you would have to put your coordinates into a column vector of 3 by 1. But again, you'll be looking at this in detail in the course. And on top of that, what would you do if you had successive transformations? Well, the power of matrices is you can actually work out a single matrix that represents a combination of transformations. So, for example, here, if I said to you, reflect a line in the a shape in the line y equals x, and then a 90-degree clockwise rotation, if you multiply the 2 matrices together, and if you look carefully, it is actually in reverse. There is a reason for this, and therefore you can sort of, if you think about combination of transformations, if you do it in a different order, your shape might actually get to a different place. And there is one of the reasons, the justifications of why matrix multiplication, the order you do it in, is important. So there it is. There is the answer to my question. The final 2 by 2 matrix, which reflects in the line y equals x and then turns by 90 degrees, is the matrix there on the right. So very powerful, and you will be looking at this and more stuff in much more detail in both years. Okay, so we've had a look at some matrices. I hope you enjoyed that. Something very different to what you've done before in mathematics. But now, as all mathematicians that we are, we do enjoy our algebra. So the second part of this session is we're going to do some algebra, looking at something called a summation of series and formulae. Okay, right. So if I think of the sum of the first n natural numbers, well, what are the natural numbers? They are from 1 upwards. Yeah, so if I think of adding 1, add 2, add 3, etc., up to my final number n, whatever that is. Well, first off, let's have some notation here, because in mathematics we always have some shorthand to represent something like this. And we use the Greek capital letter sigma. So that symbol there with r equals 1 and r equals n at the top is saying that we loop through whatever my expression is after the sigma sign and add. So sigma for sum. So r is just, I plug in 1 where r is, and then I add 2, and I keep going until I get to n. So there you can, I hopefully can understand how that works as a shorthand for what I wrote on the left. Right, now the formula for working this out is in fact this. So if I ask you to work out 1 to add 2, add 3, well, obviously you would be able to do that straight away in your head. But if I ask you to work out 1, add 2, add 3, all the way up to a trillion, Now that might cause a bit more of a problem for you because it's got with natural numbers there is an actual quick way of doing it, but if you can't see it, there is a formula that we can use, and there it is. So basically, and you can check it with a very small number. If I'm adding up all the numbers up to n, and I know what n is, if I plug it into that formula of a half times n plus 1, it does actually give me the sum of the first n natural numbers. So as an example, if I want to work out 1 add 2 up to 1,000, if I plug in, substitute 1,000 in for n, and substitute it into that formula, you get the answer, as you can see, of 500,500. Right, for the sum of the squares of the first n natural numbers, which is that. Now, if you can think, how would I write that using sigma notation? Well, the only difference is I've got now an r squared. So hopefully now you've seen this, it should sort of make sense how the notation works. So for this, again, there is a formula that we use. And the formula is that, interestingly. So it's 1/6, or you divide by 6, n times n plus 1. So you do the brackets first, obviously, and then 2n plus 1. So if you, any number again, for example, if I add up the first 50 square numbers, if I substitute it into that formula, you get a final answer there, as you can see, of 42,925. And the other one, which is the sum of the first n cubed numbers, as you can see there, which again has a shorthand way of writing, which is that. Now the formula for this is, as you can see there, which if you quickly look back at the sum of the first n natural numbers, you can see that this is an actual square of the expression for sigma r, which is an interesting result, which you can see and prove in many ways and geometrically as well. Now, there it is. If I add up the first 50 cube numbers and substitute it into the formula, you can see you now have an answer of there. So 1,625,625. Right. Why do these work? Now there are many ways to prove these results, but in your further maths course in year 12, you will use a particular technique of proof called induction. So you're going to learn a way of showing why these unquestionably work for whatever number you want the loop up to. But there are different ways of proving it, which is something you can have a look at on the internet. It is very interesting how you can actually prove these in different ways. So let's work out. I want you to, using this sigma notation now, what I would like you to do is work out these particular values. So remember, you can use the formulae for them. So I'm going to give you the formulae. So there it is. Sigma r is there. Then you've got the sum of the square numbers, which is that one, and the cube numbers, which is there. Now, you do actually get the last two in the exam, so you would never have to remember them. It's only the first one that you do. Okay, so I'd like you to evaluate those particular sums for me and see how you get on. Now, obviously, some of the ones later on, the question 5, I haven't shown you, but I think, and question 3, I think you can probably see how it works. But even if you don't get the right answer initially, as soon as you see the answers, it will make sense. And interestingly, I've put there number 6. Note how I'm not looping from 1 now, I'm looping from 50. So I want you to have a think about that. Don't think the obvious. I'd like you to think carefully and see how you can work that particular problem out. If you want to stop the video now. Okay, and here are the answers. So as you can see with question 3, I hope it makes sense that if I'm adding 3 times every square number, that's the same as if I just factorize out the 3, then I add up the square numbers and then times the final result by 3, you get the answer there. So there it is, which therefore applies loosely speaking to 5. As you can see, I've split the terms up there and then work them out individually to get the final answer. And number 6, I wonder if you got that one correct. There is no other way of doing it except for actually working out the sum, because this formula is for 1. All these formulae, as you can see in the blue, are from 1 to n. There's no way of actually shaving off the value. So the only way I can do it is work out my sum from 1 to 100 using the formula, but then I've got to subtract away all the numbers up to 49 so that I've got the 50 looped in my final sum. So there we are. So that's how you do question 6. Okay, so now that you understand how the sigma notation works and how to sum the numbers together and using the formulae, let's make it more interesting now, because what you will be asked is the following. So this is where the algebra really comes into play now. So what would be our summation formula for this particular series? So we've got 1 times 2, at 2 times 3, at 3 times 4, and we continue this to whatever number we choose. So we're going to call it n times n plus 1, where n can be any number. Right, so the first thing we're going to do is we're going to write this again in sigma notation. So I hope you can appreciate that. So by looking at the nth term, that is our expression in R in the sigma form. And again, I'm looping from 1 to n. So if you look at that and then match it with the series above, you should be able to see that working. Okay, so, right, how am I going to work out this formula now for which, instead of actually adding them up in succession, which could take a long time depending on what the number is, what is the actual single formula? If I know what n is and I can put the n in, what is the formula that will actually give me the final answer? So if you look at this carefully, so first of all, I expand the brackets, and now this is the reason why I showed you in the last exercise in question 5, we can split it. So now I've got the individual formulae for these, as you can see. So there is my 6n times n plus 1 times 2n plus 1 for sigma r squared. And then it's half n times n plus 1 for my sigma r. So there is the actual formula. And this is a completely fine formula. It does work. If I ask you to work out up for this particular series up to 1,000, if I put 1,000 into that expression there, it would give me the final answer. But let's take our algebra one step further, and they do, again, this is something that they will ask in exams, and again it's about seeing your expression and making it easier to work with, more elegant to look at, and in turn it is simpler to use. We're going to write that expression as a product of linear factors. So what do I mean by that? Well, the key is I'm going to do the following. I'm going to factorize terms from each term, expressions which are common to both. So if you look carefully, in both expressions, I've got an n and an n plus 1. Now I've got this fraction there. One is a sixth and one is a half. Now, if I actually convert that half into 3/6, then I can actually factorize out a sixth as well, as you can see there. So there is my 6n times n plus 1. And then I deliberately put it into blue so that you can see that they're the ones that are different in the two parts. So if I take out this common factor, what you're left with from the two terms is 2n plus 1 plus 3. So if I therefore then obviously simplify that expression in blue to get 2n plus 4, which in turn there's a common factor of 2 in that single bracket, which I can then factorize out. So I'm now looking at the green 2, and therefore I can then simplify that with the 6 at the beginning, because I have in effect got 2 over 6, which therefore simplifies to a third. So if you look at this carefully, and you do need to look at this carefully just to follow what I've done, that complex expression at the start of the black arrow now is whittled down to a product of three numbers, which is a third times n plus 1 times n plus 2. So I hope you can appreciate that's actually much more easy to interpret. If I know what my n is, I can very quickly substitute a value into that expression to work it out. So here I have an example from the same series. What is the addition from 1 times 2 up to 100 times 101? Well, now that we've got this formula, I can see that my n, so that's what I got from before. There's the third n plus 1, n plus 2. Now that I know that n is 100, I substitute it into that formula, and look how much simpler it is. It's just 100 times 101 times 102, and then clearly divide that by 3 at the end, and you get the final answer. So much more simpler to use and simpler to read. Okay, so you can see how suddenly our algebra is picked up the pace, and all the algebra we'll be doing in further maths is going to greatly help your regular mathematics as well. And it's a lot of fun. You can see there's lots of different techniques that you can use when you're looking at expressions, and you'll be seeing a lot more of this in the course. But here we are. Here's a question for you to try. So there it is. You've got the series at the start in part A, and you're going to work out the formula for that, and then you're going to use it to evaluate a particular example of that series. As always, I'll give you the three formulae so that you can use them in your answer. So if you want to stop the recording now, before I show you the answer. Here's the answer. So here's question 2. And I'm going to show you the answers now. So look carefully at how I've done it. So I hope you've learned. So the key is that 4, which cancels some of the fractions down, well, both of them actually, to give me a particular expression. And note how I can again factorize common terms. So look at this carefully, and you can see that I'm left with one of the brackets being a quadratic, which I can factorize. And there it is. There's the final summation formula for this series. Quite a nice, elegant one where it starts from n minus 1 and goes up n plus 1, and n plus 2. So nice expression to finish for that particular formula. And here is question 3. Stop the recording now, please. There's the answer. And question 4. And here's the answer. So again, these 4 questions I've chosen for you all got slightly different skills for your algebra and the techniques that you've learnt and gained from this. So have a look at it again carefully to see how I've done it. Now I hope you've enjoyed that taster with the matrices and the summation of series, but obviously this is a full A level, and there is so much more you're going to learn in both years, which is a precursor, hopefully, if you're going to study mathematics at university. Clearly, it's a vast subject, but further maths itself is extremely interesting. It won't be difficult, but I think that's why we enjoy maths, because it is a challenge. So, yes, here's another thing you will be looking at. This is year 13 work, but I thought I'd show it to you. This is Eulers Identity, a famous mathematician, and this is regarded as one of the most beautiful equations in maths. And there it is. And what's interesting about it is that you're using within this, you've got the two irrational numbers that occur in nature. You'll see E in your regular maths course. You will be using it a lot, as well as in further maths. And if I raise this irrational number to this power of I, where I is the square root of -1, and you've already looked at complex numbers in one of the sessions previously, and you multiply I by pi and use that as the power of this other irrational number, well, in effect, it's equal to -1, which is an incredibly fascinating result. So there it is. So you've got all the basic numbers. You've got 1 and 0, the two irrational numbers, and the square root of -1 with an add and an equals combined to give you this particular equation. Now you'll be looking at this in year 13. Will you be looking at, if I'm just following the theme of complex numbers? Yeah, so square root of -1, something that you thought was if you got a math error on your calculator because you couldn't solve the quadratic formula, when in fact it isn't something that should be ignored. It's quite the opposite. It's extremely important in not just in mathematics, but in all areas of science as well, and used extensively. Here is an example. Now, again, bizarrely, if I pass an angle and times it by the root of -1, and I work out the cosine of this particular imaginary angle, should I say, then what you get is the hyperbolic cosine of this angle. Now, again, this is something you will be looking at in year 13, but what a hyperbolic cosine curve describes is a hanging chain. Any chain or any string or anything that's suspended from 2 points describes a hyperbolic cosine curve, which is called the catenary curve. It almost looks like a quadratic, which in some ways it does slightly, but the exact curve is the Koch curve, as we call it. So again, a fascinating result, and yeah, you'll be looking at these in detail, as well as all the other hyperbolic trig functions as well. Yeah, please study further mathematics if you are interested. If you want an academic challenge, it is extremely interesting, and if you do want to study at one of the top universities, any of the STEM subjects, then it's almost a requisite. So I would definitely look carefully at university requirements to see if you might need to study further maths. Obviously, it goes without saying, to study mathematics, it is not always a requirement, but it will massively help when you do go to university. Please go to that link and you can get in touch with the Further Maths Support Programme if you do want to study further maths and possibly your school cannot provide that education for you. Okay, I hope you enjoyed that. Thank you. Diolch yn fawr.